Good morning, everyone. Morning once again, and thank you for taking me through what you did yesterday. So now I know that I'm just going to go through the assumptions that we normally make when we are modeling. Let me just share my screen. I don't know what screen you're seeing because I have a lot open. Are you seeing introduction to?
Not yet.
Not yet.
Yeah, but it showed it was coming at least. Something was coming.
Okay, let me try to share again. Are you seeing something now?
Yeah. Common
Okay.
assumptions in mathematical modeling.
Oh, yes, this is what I was requested to talk about, the assumptions we make in mathematical modeling. And hearing what you did yesterday, I think this is a perfect topic to look at today. I know that you went through the basics of modeling, how you categorize the population when you're coming up with the model. So I'll just take you briefly back about the process of modeling, then you know why we need to make assumptions as we do modeling. I know I've taught some of you before, Betty Chivumbi Nanyong at the Department of Mathematics, Makerere University, and I specialize in mathematical bioeconomics, and that's when you look at economics of diseases, or what you call health economics, but using mathematics to study how diseases economically affect nations, of the burden of the disease concepts. I do a lot of mathematical modeling for most of the epidemics, of most of the diseases, even endemic diseases. I know you know the differences between the three. And in most of the modeling that we do, we have to make assumptions, and you're going to see why. So I know you defined this yesterday. But mathematical modeling is the process of creating a mathematical representation of a real-world scenario to make a prediction or provide insight. There is distinction between applying a formula and the actual creation of a mathematical relationship. So as you looked into the basic mathematical models, I know you could tell that you are trying to create relationships between the different categories of people as you have disease in the population. So mathematical modeling is just changing a real-world scenario such that you can provide insight. And most of the benefits that we know of mathematical modeling. Okay. Are you seeing full screen now?
No, not yet.
Not yet. You're still seeing a small screen?
Yes, Prof.
It shows a screen this side. I don't know why.
Should go probably to slideshow.
Let me see. And now?
It's not yet. Not yet.
You don't see a full screen yet, or you don't see anything?
We see something, but it's not a full screen.
Actually, on my screen, I see a full screen, but I'm able to see the next slide.
Let me first fix this one now.
Okay.
So are you seeing a full screen or not? Hello?
It's not yet a full screen.
Okay. I don't know what I have to do. Let me see what I can do. I think it's now fine.
Yes, it's now fine. Thank you.
Okay. So I know you defined mathematical modeling yesterday, and as we go through the process of changing real-world scenarios into mathematical relationships, we have to simplify because you cannot model or you cannot represent a real-world scenario into mathematics completely without leaving out some facts. So in order to be able to do that, we often use assumptions to focus on the interests or on the reasons why we are modeling. We use assumptions to focus the research or to focus the problem and leave out what we think is not important to the current situation. So that's the main reason why you have to change or you have to use these assumptions. And as you see the reasons why we do modeling or why we have to change a real-world situation into mathematics, we need to gain insights into mechanisms that influence disease spread and link individual scale or the clinical knowledge with population scale patterns. And there is no way you can exhaust such a relationship if you don't make simplifying assumptions. We need to focus thinking. Model formulation forces clear. The model formulation forces clear statement of assumptions and hypotheses. I know you went through this yesterday. You have to make some assumptions before you come out with a mathematical model. And we model diseases because we need to derive new insights and hypotheses from mathematical analysis or simulation. Or for us in mathematics, we just sit in front of a computer and use available software to study a biological process, whereas they might have to do some clinical tests. For us, we don't need to do that, but we use their data to do that. But in order to be able to get meaningful insights or to get new insights and hypotheses, we have to focus the research. So we also model to establish relative importance of different processes and parameters, to focus research or management efforts, and thought experiments or what-if questions, since real experiments are often logistical or ethically impossible. For example, you might want to study maybe what happens inside the heart of someone, or what happens when you get a bite from a mosquito. We know that once you're bitten by the mosquito, the parasites first go to the liver and will be there between 2 to 3 days. So if you need to know what happens inside the liver, that means you have to cut up somebody, which is ethically impossible or ethically unwarranted. So in mathematics, knowing the time it takes the parasites to reach the liver, knowing the processes of the immune system, knowing the reproduction rate of the parasites, you can sit down and say, within 2 days, this person is going to have this, for example, the parasite burden, or they are going to have this number of parasites in the system. And if you don't do this, this will happen, which you cannot do through experiments. But the beauty of mathematics is that you can explore management options by just looking at the numbers or the days. Then you tell within this time you're going to have this. Then you have to know that we don't usually say we'd use mathematics to predict future trends, because they are the models are highly simplified representations of very complex systems, and parameter values are difficult to estimate. And quantitative predictions are virtually impossible. But they guide you, they guide management options of what you need to do with the numbers. We look at the input numbers and what to expect to output. So in brief, models are very important in forecasting, but it is impossible to do all if you just have a model that models every aspect of the system that you're looking at. This I know you did yesterday, the components of mathematical modeling. You have to identify and define the problem or problems. Then you have to make assumptions. When you make assumptions, you're identifying important variables. You apply mathematics to solve problems. You verify and interpret solutions in the context of the problem. You verify and interpret your solutions in the context of the problem, and then you validate the model and refine the mathematical model. That is, if you feel the output of your model doesn't align with the known literature, then you have to refine your model until you report the findings or the true findings that conform to the known literature. So what decisions do you make when you're designing a model? All of this goes to the underlying assumptions, and we are going to briefly go through the assumptions the common ones that we make. So all these have to go to the assumptions. What kind of population are you trying to look at? What is the disease? How long do you want to study this? This guides you to what assumptions you're going to make to simplify the biological process. So even after your compartmental framework is chosen, you still need to decide the frameworks you went through yesterday. You still need to decide whether you're going to use the deterministic or stochastic. And this always goes with the assumptions that you make. Are you going to use a discrete or a continuous model? Are you going to study this process every minute or in a day? Discrete versus the continuous state variables. Are you going to use variables that change every unit time or continuous ones? Are you going to assume all these as assumptions? Are you going to assume a random mixing or structured population? Random mixing is when we assume, even as we are here, we can easily or randomly mix with anyone in the population. But we know that's not possible. So are you going to use that? And if you take that up, what is the underlying assumption that you're making? Or are you going to do a structured population? Are you going to assume homogeneous or heterogeneous? Homogeneous mixing is when you assume we can easily mingle with anyone, even as far as Mbara, for example. But this is usually not the case, but we always assume homogeneous mixing, and we shall see the reasons why, or why you need to make such assumptions.